Hey everyone, let's talk a little bit about centroids. And I'm going to begin the discussion actually by looking first at a seesaw situation. So let's assume I have two people, a large person over here on the left and a smaller person over here on the right. And I want to balance them on a plank. And we're going to assume the plank has no mass, just to make life simple. And then I'm going to have a fulcrum at some location. And if they're balanced, if I've got them balanced, then the fulcrum is going to be closer to the larger person. And the idea behind this is that the net moment, the net torque around the fulcrum is equal to 0. So if the net moment is equal to 0, then the moment is equal to force times distance. And so I probably should have a G in here, but I didn't. I apologize. But let's go ahead and just put it in. So we'll multiply all of this by G, and then we can see it doesn't matter because there's a 0 over here. But the weight, so that's the force of the person on the left, and that actually should be positive, and this one is negative, right? So the weight of the person on the left is exerting a counterclockwise, so positive moment. So that's mass 1 times G times x1, right? So that's in that direction. And then the weight of the person on the right, is mass 2 times G, and then times x2, so the moment is m2G times x2, and that's going to be counterclockwise, and so that's negative. Okay, and so the idea here, if I cancel out the G, is I should be able to find out this net moment as being equal to 0. But what if, just for the sake of argument, this is x equal to 0, then x1 is actually a negative quantity, right? And so what do I end up with? I'm going to get rid of the G because it's a 0 over there. I'm going to have 0 equals m1, and I'm going to put a minus sign out in front of here, times the absolute value of x1. Because that's a negative value, hence the minus sign out here. But I'm only considering its size. Okay? So then minus x2 is positive, so m2 x2. Right? And so what we find out then is that 0 is equal to, because the minus signs will go away, m1 x1, magnitude of x1, m2 x2. And so this is telling me that when I add these together, I get 0. Well, what's at 0? Well, 0 is the center of mass of the system. Okay, so the mass centroid, that's not a real term, but I'll make it up here. The mass centroid of the system is here. Okay, and so I'm able to get something about the mass centroid of the system based on this right there, okay? So let's take a look at what's actually a centroid, okay? So centroids are going to be based on areas, okay? Centroids are based on areas. So I'm going to say I want the centroid of an area. And I'm going to leave that bottom there just for a little minute. So the centroid of an area. So the idea here is if I want to know the centroid of the area, I need some sort of an equation. So what I do is, like the masses, I'm going to look at areas. And I'm going to look at the positions. Well, so here is an area right here. Okay, and so that blue region has an area. And what's that area? Well, the area is base times height. Well, the base is delta x. And the height is f of x sub I, because the area is located at some region x sub I. The area is located at some point x sub I on the x-axis. And it has a height. This is some function f of x. The height is y. Y is f of xi. Right? So y equals f of xi. And so what I do is I take the position, x sub I, like I did here with the moments, the mass, center of mass. Here's the position, and I multiplied by mass down here. I'm going to multiply by area. So it's going to be f of x sub I times delta x. And so when I want the centroid, at least along the x-axis, of all of these points, I have to add them all together, right? And so that's a summation. So it's a summation, right, of x sub I, f of x sub I, times delta x, I equals 1 to n, where there are n of them, which you know as as this approaches infinity, right? As this approaches infinity, and actually, I'm going to even change this a little bit. I'm gonna write this out as summation I equals 1 to n of x of I times the area, right? So area, but I'm going to put a little dA there. Not dA, let me call it delta A. So delta A is the area of this rectangle right here, okay? So that has an area, delta A. And I'm going to add all of those together. In fact, maybe I'll even put a delta A sub I. Okay, so delta A sub I. All right, then, if I make n approach infinity, my delta A sub i's are getting tinier, right? And this becomes, okay, so this is the limit as n approaches infinity, and this becomes an integral of x dA. And that's going to be x centroid. That's going to be the centroid along the, where is the centroid along the x-axis of this area, the area underneath this entire thing? Where is the centroid of that area? Now, as I look at this particular function, I would anticipate it's going to be somewhere off to the left of middle. Why? Because there's more area on the left. Just like the centroid is closer to the heavy person than it is to the lighter person. Okay? So that'll give us a start on what we're going to do with centroids of areas, and we'll get into more detail here in a little bit. Right? If you have any questions, please leave them in the comments below. Thank you.